Okay, so we have talked about these logic families basically. Okay, diode and uh, so the building blocks of this logic family is uh, diodes and resistor. Okay, here it is diode and transistor. Okay, and here we use transistor as the main gate. Okay, but sometimes diodes and resistors are using normally. Okay, but the main function is handled by the transistor. Okay, actually these are bipolar transistor. Okay, so this TTL family is a bipolar transistor logic family. Okay, and also ECL. Okay, emitter coupled logic. Okay, that one also based on bipolar transistor. Okay, so this TTL and ECL are based on bipolar transistors. Okay, and this one is the most popular one, I hope. TTL, transistor logic. Okay, and we have another logic family is called CMOS, complementary metal oxide semiconductor. Okay, so these are based on MOSFET, actually, field effect transistor. Okay, so these are the CMOS logic family based on MOSFET transistor, but this TTL as well as ECLs are based on bipolar transistor. Okay, so I think this one TTL and CMOS are the most popular one. Okay, so there are, so we have seen some logic operation, the circuit operation of these two, and sometime we have seen this one also. Okay. How we can construct a digital logic circuit using this kind of component. Okay, so I think now you have idea about that. Okay. Can you hear me? Okay, thank you. Okay, so okay, now today we will so you know that so these are different logic families, no? These are different logic families, so that they should have different characteristics. Okay, different characteristics because they are belonging to different logic families. Okay, so we use some parameters to characterize them. Okay, so these are the characteristic parameters. Okay, these are the characteristic parameters we normally use to characterize a digital logic device. Okay, so if you see any data sheet, okay, of digital logic IC, okay, you will see these parameters. Okay, okay, so we will see this. So we are not going to prefer all these parameters. Okay, we will see some basic important parameters. Okay, so I think this one is important parameter. Okay, so before that, I think in previous week I have explained you that. Okay, so if we have a logic device like this is a logic device. Okay, this is a logic device. Okay, and there can be many inputs. Okay, there can be many inputs as well as there can be many outputs. Okay, so these are inputs. Okay, and these are outputs. Okay, so you know that this is a electronic device. No, these are electronics device. So normally electronics devices are classified according to or characterized characterized according to normally voltages and current. Voltages, current, impedance. Okay. So normally for electronic circuits, we use these parameters to characterize electronic circuits. Okay. Because these parameters are only understandable by electronic circuits. Okay. So we already know that. Okay. So here we have input and output. If you consider logic device, okay, you will have input as well as output. Okay. So normally there are two ports, input ports and output ports. Okay. So, so you can see that, and also you know that this is a logic device, no? Okay. So if it is a logic device, digital logic device, it is a digital device. Okay. Digital device. Okay. So there should be two voltage levels, no? There should be two voltage levels. Okay. And so one level is high voltage level. Okay. So one is high voltage level, and other should be a low voltage level. Okay. Other should be a low voltage level. Okay. So this is a device, logic device. So you will have high voltage level and low voltage level basically, and you will have some input and outputs. Okay. So you can define some parameters based on this based on these factors. Okay. High voltage level, low voltage level, and input output. Okay. So you know that we have, if we are using a logic circuit. Okay. So sometime if you want to give a voltage here. Okay. So sometime there will be a current, input current. Okay. There will be input current. And if you connect this logic circuit, so output to another circuits, okay, there should be another circuit or load. Okay, there should be output current. No. Okay. So basically we will have some inputs and output currents. Okay. Inputs and output currents. Okay. So these inputs and output currents are normally defined according to this high voltage level and low voltage level, because these are different. Okay. Okay. So I think you can understand. Okay. So here we have defined high level input current. Okay. High level input current. Okay. So it is IH. Okay. Input high. Okay. So that means you have a logic device. Okay. And if your input, if you set this input pin to high voltage, okay, to high voltage, there can be a input current. Okay. So that is defined as high level input current. Okay. I think it is clear. Okay. Very simple. Okay. And basically we know that input current means that current is going into the device. Okay. Normally input current means current is going inside the device. Okay. So normally when we are talking input current, we normally consider the plus direction into the device. Okay. So plus direction is normally, that is a normal way. Okay. Common way. Okay. So input current, if the input current is inside the logic circuits, it is considered as plus current. Okay. And sometimes it can be outside. Okay. Is that true? Can it be minus? That means can it come in out of the device? Can anyone answer? If the logic device is there, okay. So if you connect some voltage here, okay, voltage here, okay. So is it always input? Is the current is always going inside the device, or can't it come out of the device? Can anyone just, what is your opinion? Can anyone answer, please? Actually, sometime current can be coming out of the device. Okay, so it is happen like this. If you give, so there, yeah, it can be come out of the device. Okay, because if you given the VCC, okay, there should be a operating current. No, so these are based on active device. Okay, active device. Active device means we have to give a supply voltage to activate them. Okay, so sometimes this VCC can be higher than the input voltage. Okay, so at that time, sometime with this pin, inside this pin, there can be induced voltage. Okay, and that induced voltage is higher than this voltage. Okay, our given voltage, our input voltage. At that time, sometime the current can be come out of the device. Okay, current can be can come out of the device. Okay. 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 So okay. So this is high level input current. Okay. Okay, and as well as we can define the low level input current. Okay, so this is low level input current. Okay, so you can understand what is the low level input current. That means if the given voltage is low, at that time also current can be going inside or outside the device. So it is referred as low level input current. Okay, so these are high level input current, low level input current. Okay, and okay, so these are the output currents. Okay, so these output currents are also defined with respect to low voltage level and high voltage level. Okay, so if the voltage is high, okay, if the voltage is high, it is high level voltage is high, and if there is output current, that is referred as output current, high level output current. Okay, and if the voltage is low, and if the current is if there should be a output current, and it is defined as low level output currents. Okay, so I think these are understandable by you. Okay, so this here you can see some values are there. Okay, values are there. Okay, so we will see them also. Okay, and also sometimes this output current, okay, sometimes this not sometimes, normally this output current is used to decide the number of input. Okay, number of input with respect to output. Okay, so that is called actually fan out. Okay, that is called actually fan out. And I think this parameter is also there. I'm not sure. Okay, but anyway, we will discuss it later. Okay, so this current is used to determine the fan out of the logic device. Fan out means number of inputs per one out, as I can remember. Okay, I think that should be there. Okay, we will check. Okay, so that is called fan out. We will see. Okay, so okay, so I think one example is also there. Okay, so you can see that. Okay, You can see that normally output current should be coming out from the device. Okay, so it is not inside the device normally. Okay, it should be come out of the device. Okay, because that is why, because we called it output current. Okay, so if it is output of the device, it is considered as plus. Okay, it is considered that as plus if the current is outside the device. Okay, so you can see that here you are given minus value. Okay, so how it happened? Can anyone explain that? Okay, and also note that this is high level output current. High level output current is referred as minus 400 microampere. Okay, so anyone can explain how it can happen?
That is what you have to see. That you have to see what is my requirement based on my requirement. You have to come with the hardware. It is not that you select the hardware and then given the system, how do you do hardware? That is the way you have to do, right? And then let's look at what are our system requirements and what are the.
And also you can see that for a low level output current, okay, low level output current, it is given as plus milliampere. Okay, so here the current is also high. Okay, can you explain these things? How it happened? Okay, and here also you can see that. Okay, here also you can see that it's not good.
What is your original scope? What is your individual scope there? What do you do?
Okay, can you hear me? Again, my connection is dropped. Can you hear me? Kindly feedback someone. Okay, thank you. Okay, so okay, so you can see that. So here you can with these parameters, you can note two things. What are the two things? When it is high level output current, is minus 400. Okay, minus 400 microampere. And low level output current, IOL, low level output current is plus, and it is 16 milliampere. Okay, so you can see that this current is lower than this current. IOH is lower than this current, and it is inside the device. Okay, so we can explain it in this way. Okay, so you can see that we have a logic device. Okay, and we have some output pins. Okay, so these are output pins. Okay, okay, so if the voltage is high, here, okay, if the voltage is high, voltage is high, sometime that voltage is greater than, so this is high voltage, no, that at that time this given voltage can be higher than the voltage inside the device. Okay, voltage inside the device is lower than this input current. Okay, input voltage. So at that time the current can be flow inside the device. Okay, so this output current can flow inside the device. Okay, so it is happening actually. Okay, if we give a high voltage here, if that voltage is greater than the inside voltage, sometimes current can be go inside the output current can be go inside the device. Normally output current should be out of the device. Okay. But sometimes it can be go inside the device. Okay. So at that time, it can be minus. Okay. It can be minus. So I think it is okay. Okay. So if you are given a low voltage, sometimes that low voltage. Okay. So if you are given a low voltage here, if you are given a low voltage here, okay, if you are given a low voltage here, okay, if you are given a low voltage, okay, so sometimes this low voltage is less than the inside voltage, okay. So this voltage may be high and this voltage may be low. So current can come out of the device. So it is mentioned as plus because output current is normally outside the device. Okay. So it can be, we can have plus current, output current. Okay. At the low input. So it is happening, no? Because here it is 16 milliampere. Okay. So that is, you can explain like this. Okay. And that way you can explain this minus and plus things. Okay. So how can you explain this? So you can see that when the voltage is high, current is low. When the voltage is low, current is high. How can you explain that scenario? When the voltage is high, current is low. You can see it, no? If the high voltage is there, the current is 100 microampere, 400 microampere. But the voltage is low, current is 16 milliampere. That means current is high. So how can you explain this? Actually, sometimes this happen in electronic circuits, okay? When we given the voltage, if we increase the voltage, the current can be low. Okay. And if we reduce the voltage, current can be high. Okay. So in power supply, sometime in power supply, this can be happen. Okay. So how can you explain that one? Actually, it is because if the power, okay, if the power of the device is almost same, power is VI, voltage into current. Okay. So if you have a constant power, dissipation power, if you increase the voltage, sometimes current can be low. Okay. Because you need to maintain this power in a constant value. Okay. And if a voltage is low, current can be high. Okay. Because you need to have a constant power. Okay. So in that way, you can explain. Okay. So that is maybe not 100% correct. Okay. This theory, this is not 100% correct for every instant. Okay. But some instant, some cases, this is true. Okay. So normally this is happening like this. Okay. When we are talking about rated voltage and current, this can be happen. Okay. Okay. I forgot to tell one thing here. Okay. So you can see that this output and this high level, low level input current sometimes define using unit load. Okay, unit load. So that is the current dissipated through a unit load. Okay, so that is the idea. The current dissipated through a unit load. Okay, so sometime in data sheet, this input currents, low level and high level input currents are given with respect to or in terms of this unit load. Okay, so we will see them later. Okay, okay, so you can see that. Okay, when we check the data sheet, sometimes this low level input current, low level and high level are given with respect to unit load. Okay.
So what you have to do is now you have to
Okay.
check.
So I think basically we have seen now two parameters. Okay. Input current and output current. Okay. Input current and output current. And this input current is defined in two occasion. That is input at high and input at low. So this also defined in two terms, output at high and output at low. Okay, so I think it is clear. Okay, and so this is office state. Actually, now we are not going to talk about this one. Okay, because this is tri-state logic function. This parameter is related with the tri-state. Here we are talking about two-state logic function. Only high voltage level and two low voltage levels are there. Okay, only two levels. Okay, but in a tri-state logic device, okay, logic function, you will have another state called high impedance state. Okay, so this is high level of state related with that tri-state logic function. Okay, actually that is the when the input is high and the voltage level is high, the output current. Okay, so that is defined like this. Okay, the output current the when at high state impedance and high voltage level. Okay, so these are we are not going to talk. Okay, just have idea about that. Okay, because these are relevant to tri-state logics. Okay, so we are not normally going to see these. Okay. Okay, and I think these are also very important, these four. Okay. So I think you have already know that this one. Okay. So I have explained, you know that. Okay. If we have a logic circuit, you have an input port and you have output port. Okay. So there should be some voltage, input voltage and output voltage. Okay. And this voltage are also related with two status. No. Okay. So there can be voltage input low, voltage input high, and at the output also there can be voltage output low, voltage output high. Okay. So in that way you can define another four status. Okay. Input low voltage, input high voltage, output low voltage and output high voltage. Okay, so I think it is clear. Okay, and I think this is very important. Okay, because normally operation of the, so this is mainly affected to the operation of the logic circuit. Okay, to have a good operation, to have a expected operation without error, we have to give this voltage level accurately. Okay, otherwise that logic function is not working, that logic device will not work. Okay, so we will see some details about this. Okay. Okay, so okay, so I will take, okay, I will take a TTL logic circuit. Okay, I will take a transistor logic circuit. Okay, so you have inputs and you have output. Okay, here you have input and you have output. Okay, so 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 in the TTL logic families, okay, this input voltage, okay, input low voltage is around 0.8 volt. Okay, So we set this maximum voltage. I will tell you why we called it maximum voltage. Okay. So this is called actually maximum input voltage. Okay. Maximum input voltage. That is 0.8. Okay. And there can be, so this is in low state. Okay. So there should be a input voltage at high. Okay. So it is called as 24. So normally for TTL, it is 24 volt. Okay. And we call this minimum input voltage for high level. Minimum high level input voltage. Okay. And this is called maximum low level voltage. Okay. So anyone can tell me why we use this maximum and minimum terms here. If it is high level, we define a minimum voltage level. And if it is a low voltage, we define the maximum voltage level. Maximum input voltage, and here we define the minimum voltage. Why is that? කාටහරි කියන්න පුළුවන්ද ඒක? So can anyone tell me how we can define this maximum and minimum input low level voltage and input high level voltage? Okay, I will tell you that one. Okay, so actually up to this level, okay, up to this level, we have talked about two voltage levels now. We have talked about two voltage levels. Okay, one is high voltage level and one is low voltage level. Okay, so sometime we so up to this level, okay, up to this level, and also for your design, you have assumed that, okay, you have assumed some constant voltage level for these two voltages, no? Okay, for example, you can assume 5 volt as high level and 0 volt as low level. Okay, so we have only these two voltage level. Okay, okay. So if you have a device and if you give a 5 volt here, it is considered as a high voltage 1 or 0. Okay, we don't know. Okay, it can be 1 or 0. It is as you define. Okay, so high voltage level you can define as 1 or 0, and low level voltage level also you can define as 1 or 0. So it is depend on your definition. Okay, you can define it, okay, in your application. Okay, so up to this level you have considered two voltage level. Okay, so you can have a 5 volt. It can be a, for example, we will think that this is 1. Okay, this is 1 and this is 0. Okay, and it can be changed also. Okay, it can be changed, please understand. Okay, so if you want to give a 1 here, you can set this pin to 5 volt. Okay, and if you want to set 0, you can set this pin to 0. Okay, very simple. Okay, you can do that. Okay, but sometimes in digital, in our circuit, that in our normal circuits, okay, we have some interconnected device, no? Interconnected device. Okay, so some device output can be given as an input of another device. Okay, so some input, some another equipment output is connected to input of another device. Okay, so it can be interconnected. Okay, for example, if you have a AND gate. Okay, for example, if you have a AND gate, it can be the output of the AND gate can be connected to another XOR gate. No? Okay, so it is normal way. Okay, so devices are connected, interconnected to form a desired electronic circuits. No, okay. So you can see that here. So for this device, we can set the voltage, no problem. Okay, we can set the voltage 5 and 0, no issue. But output, we can't guarantee that there can be a voltage drops. No? So we can't guarantee that this can be 5 voltage. Okay, if you want to have one here, we can't guarantee that this can be a 5 voltage. Okay, it can be higher or low. Okay, so if you have amplifiers or something, it can be higher. If you have attenuation effect, it can be low. Okay, so you can't guarantee that always these inputs are 5 volts and 0. Is it okay? ඒක තේරුණාද කියප එක? ඒ කියප එක තේරුණාද? If you couldn't understand, please tell me, okay? So what I want to tell you is that although we have set 5 volts as 1 and 0 volt as 0, we can't always give this voltage level. That voltage level can be changed inside an electronic circuit. Okay, so it is happening when we are communicating a bit stream. Okay, so if you want to send some bit stream, okay, let's say that you have a memory here. Okay, you have a memory here. Okay, and this is your memory. Okay, so stored, you have stored some data here. Okay, let's say that you have installed some voice here. Okay, so it is installed as a digital data 1 and 0. Okay, so you have some 1 and 0 bit stream in this memory. Okay, so now you want to get the output of that voice. Okay, you want to get the sound. Okay, for that one, you have to convert this digital signal, digital data into analog data. Okay, so you can use a digital to analog convert. Okay, digital to analog convert. Okay, so if you feed this data through a line wire, okay, wire to the DAC, and that will give you the analog output. Okay, so that analog output you can connect it to the speaker. Okay, then you can hear the voice. Okay, because voice is analog device, analog analog parameter. It is not digital, but we have converted to digital and we have stored. Now we convert it back into analog again. Okay, for that one you have to send this signal from this memory to that. Okay, so it is also a communication. No? It is also a communication. Okay, because that data is sent from this device, from memory device to the DAC, other device. Okay, so you have sent this data, okay, some distance. So it can be very little distance. Okay, maybe 5 millimeter. Okay, maybe 10 millimeter. But anyway, you have sent it to distance. Okay, so we have sent this data. So when this data are traveling from here to here, that can be affected. That can be affected by some fact. Maybe that data can add some noise, or that data can be distorted. Okay, and here you reach some distorted data. Okay, for example, if you have sent like this, okay, so your data is 0, 5 volt, 0, 5 volt, 0, 5 volt, like you send. Okay, but actually you received, okay, you received එකට අපි අල්ලන්නේ ගාන ලැබුණු දෙයක්. ආයෙම. ඉතින් මම මෙහෙට වෙලා වැඩේ කරන්නේ. මෙතන කරන්නේ දැන් මෙතන ඉක්විප්මන්ට් එක මම සංකාරය වාහිනිය අපරාධ මේ කාලේ. බලන්න. කොහොම හරි කරන්න තනක් හොයාගෙන. Okay. So you have sent this kind of signal. Okay. This is the output of the memory. 0.5 volt. Okay. Okay. But when it travel, okay. So this can be like this. Okay. So some attenuation happen, some noise added, and that is distorted. Okay. Okay. So here you can't define very clearly 5 volt and 0 volt. You can't very clearly define. Okay. So there can be some shift of voltages. Okay. So that can be happen in a device that is actually happening. Okay. So although we have expected to have this kind of two, okay, this kind of 2 voltage level, sometime we will have other voltage also. Okay. So we have to define these. Okay. So we have to get account these effect also. Okay. So practically, okay, if you have a device, logic device, okay, if you have a logic device, okay, so if it is the input pin, okay, input pin, okay, so let's say that this is a low voltage. Okay. So you have to give a 0 voltage here. Okay. 0 voltage here. Okay. So you will have a 0 voltage here. Okay. But sometime it can be changed. Okay. Sometime it can be lower than 0 voltage and it can be higher than 0 voltage. Okay. So when you are considering the low voltage, okay, I'm talking the low voltage. So it can be higher or lower than 0 voltage. Okay. It can be minus value also. No? Okay. Sometimes this can be a minus value. Okay. Because if you send this 0 voltage, okay, so some effect happen and it can be a minus value. Okay. It is not 0, it can be a minus value. Okay. So sometimes it can be minus also. Okay. So, okay. So you can see that no? If it is lower than 0, if it is lower than 0, okay, it is okay. No issue. Because it is lower than 0. So again, you will have the 0 effect here. No? Okay. So if that voltage is lower than 0, it is okay. Okay. But if it is higher than 0 at that time, that is the issue. No? Okay. For example, if you, so you expected 0 voltage here and you received some another voltage, 2 voltage. Okay. So this 2 voltage, you can't, this device can't identify as 1 or 0, as 1 or 0, because it is not in 0 or 5 volt. Okay. So it cannot detect it is 1 or 0. Okay. So we have to give some margin. Okay. We have to assign some margin. Okay. Actually, we are not assigning that margin. That is with the property of this device. Okay. So that is decided by the properties of this device. Okay. Okay. So I think you can understand that one. Okay. So for example, in TTL, okay, for example, in TTL, transistor logic, okay, if you given minus point voltage or less voltage, it is considered as 0. Okay. 0.8 voltage and less voltages, it is considered as 0. Okay. And if it is high than 0.8, so it will not detected as 0. Okay. So it is not detected as the low voltage level. Okay. Don't think that always low level voltage is 0. Okay. Sometimes we can define this low voltage level to 1 also. Okay. ඒක තේරෙනවන්නේ මම මේකයි මේ 01 ගන්න කැමති නැත්තේ. Okay. Because these 01s are depend on our definition. Okay. Okay, we can define this 0 as high voltage and 1 as a low voltage. Okay. Okay. So I take here as an example. Okay, I take that low voltage is 0 and high voltage is 1. With that definition, I have explained this. Okay, if it is less than 0.8 volt, it is detected as 0, and if it is higher than 0.8, it is not detected as 0. Actually, it not detected as low voltage level. Okay, that is the correct word. Okay, so if it is if you have a TTL logic family circuit, logic device, TTL logic device. Okay, if input voltage, okay, input voltage of a pin is detected less than 0.8 volt, it is considered as 0 or 1. Okay, low voltage level, it is considered as low voltage level, and it is higher than 0.8, it cannot, this device cannot detect it as a low voltage level. Okay, is that clear? So here so this is input voltage low status. Okay, so you have a maximum value there. No? You have a maximum value there. That is 0.8 volt is the maximum value. Okay, so that is the maximum value. If you have greater value than this one, it is not detected as a low voltage level. Okay, so this 0.8 is the maximum value. Okay, so in low state voltage level, input level, we have a maximum value, maximum margin. Okay, I think it is clear. Okay. Okay, now consider that so we take as 5, you know, our high voltage as 5 in this example. Okay, but if you have a TTL, okay, TTL, okay, okay, let's say that you are given 5 volt. Okay, so if it is 5 volt, it is no problem. The device can identify it as 5. Okay, but say somehow due to attenuation or something, this voltage level is reduced. Okay, reduce up to some level. Let's say that it is 2 volt. Okay, so at that time also, okay, so this voltage also, the logic device cannot understand it is 1 or 0. It is high voltage level or low voltage. Okay, so for that one also, for high level voltages also, we have to give a margin. Okay, actually that margin is not decided by us. Okay, it is decided by the logic circuit. Okay, ඒක තේරෙනවනේ. ඒ margin එක අපි නෙවෙයි define කරන්නේ. මෙන්න මේ value එක අපිට define කරන්න පුළුවන්. හරි, low voltage එක 0 කියලා ගන්නවා, 5 voltage එක low 5 voltage එක 1 කියලා ගන්නවා කියලා අපිට define කරලා. We can define it in that way. Okay, but this detected value is not, we can't define that value. Okay, it is decided by the logic device, not by us. Okay, තේරුණා නේද ඒක? අපිට මෙතන voltage එක define කරන්න පුළුවන් වුණාට මෙයා කොච්චරකට යනකල් detect කරන ගන්නවද කියන එක අපිට decide කරන්න බෑනේ. ඒක decide කරන්නේ ඒ logic device එකම තමයි. හරි. So we take this TTL as example now. for TTL, this high voltage level, if you have 2.4 voltage, this is detected as high voltage level. Okay, high voltage level. But if it is less than 2.5, it is not detected as high voltage level. Okay, it is not detected as high voltage level. It cannot detect it. Okay, so if you give 5 voltage, it is okay. And if you are given 5 volt, and when it come to the logic gates, somehow it is attenuating. And if you get 2.5 volt, you will not face any problem. Okay, because it is detected as high. Okay, it is detected as high. So you will have no problem. But the problems happen if the input voltage is less than this 2.4 volt. Okay, if it is less than 2.4 volt, you will have a problem because it cannot, that device cannot detect it as a high voltage level. Okay, so if you are given more voltage, okay, if you are given great, if you are given higher voltage level to the input, higher than this 2.4, it will be okay. No, it is detected as 1. But if you are given lower voltage, it is not detected as 1. Okay, so here you have a minimum value. No, here you have a minimum value. Okay, so that is how it happened. Okay, so in a low voltage level, you will have a maximum value, and high voltage level, you will have a minimum value. Okay, so I think you can understand. Okay, that is why we are defining these things. Okay, now we have uh, okay, so when you are, so as assignment, I have given you a given to given to construct develop a multiplexer. No? Okay, so there you have to develop a counter. No? Okay, so you can see that counters are interconnected each other. Okay, so you said that your counters are working when you have simulated it in Proteus, this counter is working, but actually it is not working. Okay, so this problem can happen because you have to interconnected counters from one to other. Okay, so if you are given the input counter is also okay, you are given 5 volt and 0 volt. Okay, but when it goes to other counter, this voltage level can be reduced because this device will add some noise and have to have also add some attenuation. Okay, so output will not the 5 volt, it will be changing. Okay, and it is worst when it come to here. Okay, because this voltage is changing and you will have output another change in output. Okay, so at that time, sometime if you have crossed this margin, if you have crossed this margin, your counter is not working properly. Okay, your counter is not working properly. Okay, that is why you have to consider the current. Okay, and these voltage levels when you are designing a circuit. Okay, otherwise it will not properly work. Okay, because we expected very fine voltage level like this. Okay, but actually we don't have voltage level like this. Okay, we will have some distorted voltage like this. Okay, so that may be one reason your design is not physically working, but in simulation these effects are not taken into account. Okay, so simulations are working properly, but the actual circuit is not working properly. Okay, okay, because of this issue. Okay, so I think now you can understand the importance of these things. No, okay, so when you are designing the circuit, you have to refer the data sheet. Actually, in the data sheet, all these are there, and you have to check one by one. The input and output parameters are according to the data sheet. Otherwise, your design will not work. Okay. Okay. So I think you have understand this one also. Okay. Low level input voltage and high level input voltage and low level output voltage, high level output voltage. Okay. So there are four things. Okay. Okay. And mm, um, so um, okay. So keep that in mind. Okay. So we will move forward. Okay. Uh, and this one. Okay. This one is also very important. Supply current. Okay. This is a supply current we have to give. Okay. So so when you are given a low and high status, this supply current can be changed. Okay. So sometime this supply currents is defining in according to that case, high level and low level. Okay. So this is high impedance level that is relevant to tri-state. Okay. Tri-state logic. Okay. So if you get AND or NAND logic circuits, you will not get this parameter. Okay. You will have this two only parameter. Okay. So this is the supply current for high voltage level. This is the supply current for low voltage level. Okay. So if you want to take the total supply current, okay, uh, just supply current, you have to get the average of these two. Okay. So you have to add these two and you have to divide it by 2. Then you will get the average ICC. Okay. And I think in this case also that is relevant. Okay. So there can be a input low voltage level. There can be a, sorry, the current. Okay. So there can be output high current, output low current. Okay. So if you want to find just output current, you can get the average of these two current. Okay. So I think it is easy to deal with the average current. Okay. For your design, when you are designing, sometimes easy to work with the average current. Okay. Okay. Uh, so that is the supply voltage. Okay. Okay. And rise time. So I think this one also very important. Rise time and fall time. Okay. So this is happen when the logic state is happen transition. Okay. So if the logic state is transit, I don't know that word is correct or not. Okay. I will set that. So transition means 0 to 1. Okay. Or 1 to 0. Okay. These are the two transition you can have in a digital circuits. No? It is changing from 0 to 1 and can be changed from 1 to 0. Okay. Okay. So, so when we are draw the waveform, we are clearly draw like this. We have 0, we have 1 like this. Okay. But actual, as you have now already know, okay, we have learned this. This waveform is not look like this actually. These waveforms are not look like this actually. Okay. Because it can, some distortion can happen. Okay. So this transition cannot happen immediately. And this is a rising transition and this is a falling transition. So these are not happen instantly like this. Okay. Sharply. There is not, actually there will not be very sharp transition. Okay. But this is okay for low frequency. Okay. For low frequency, you can get this kind of sharp transition. Okay. But when you are dealing with high frequency, this is impossible. Okay. So there can be some time taken to transit from 0 to 1 or 1 to 0. Okay. So that is defined as the rise time. Okay. Let's say that you have 0, Okay, zero means zero level. Okay, and let's say that this is a zero voltage. Okay, the low voltage. Okay, low voltage, then you will have a high voltage. Okay, so that low voltage can be zero and this high voltage can be one, and low voltage can be one and high voltage can be zero. We don't know. Okay, okay, so it is in low voltage. Okay, we have low voltage level and we have high voltage level. Okay, so when the transition happening low to high, it will take some time like this. Okay, okay, so there is a minimum, sorry, maximum or some voltage level, no, input voltage level, input to output voltage level, no? Okay, so you have to get the 100% of this, sorry, 10% of this minimum level. Okay, and 90% of this maximum level. Okay, and that time, okay, the time taken to rise the voltage from low voltage, 10% from low voltage to 90% of high voltage. Okay, that time we called as rise time. Okay, okay, so if it is not clear, we will have example, quick example. Okay, so let's say that we have a TTL. Okay, uh, TTL logic family circuit. Okay, so let's say that our low voltage level is in our circuit, low voltage level is 0.4. Okay, 0.4. Okay, and the high voltage, this is the low voltage input. Okay, okay, this is low voltage input voltage, rated input. Okay, this is the this is this is the expected our so this is defined by us. Okay, we can give low voltage as 0.4 voltage and high voltage as 4, let's say that 5 volt, 5 volt. Okay, so our low voltage is 0.4 volt and high voltage is 5 volt. Okay, and um, so we have 0 like this. Okay, 0.4 voltage. Okay, and so I will write that go like this. Okay. So this is time and this is voltage line. Okay, okay, and so low voltage is 0.4 and high voltage is 5 volt. Okay, so you will have this kind of transition. Okay, this kind of transition. Okay, this kind of transition. Okay, so if you want to find the rise time, okay, you have to get 10% of this 0.4. Okay, so what is the 10%? That is 0.04. Okay, so if you get this point, okay, let's say that this is 0.44, you have to add no 10%. Okay, so you have to add 10%, 0.4, 0.44. So this is that point. Okay, and this is 5 volt, and you have to get 90%. 90% means 4.5. So this is the 4.5. It is not clear, no? Okay, so this is 0.4, this is 0.44, This is 5 volt. This is 4.5. Okay. So you will have this kind of transition. Okay. And this is the 10% of low voltage point, and this is the 90% of high voltage. Okay. So if you measure the time difference between this one and this one, that is T2 minus T1. So this will be the rise time. Okay. This will be the rise time. Okay. So the fall time also defined in this way. Okay. So it is 90% and 10% level. Okay. And the time difference between these 2 points. Okay. Okay. For example, so here you will have 5 volt to 0.4 transition. Okay. The minus transition, it is like this. Okay. And 4.4 value is here. That is 90% of this value. And 0.44 point is here. That is 10% of low value. Okay. And if you get the time difference between these two, okay, that is, let's say that this is T1, T2. Again, T2 minus T1 will be your falling time. This is mentioned, this is defined as falling time. Okay. So that is the way we define the rise time and falling time. Okay. Okay. I think that one also very important. Okay. And this propagation delay means, so if you set some voltage at the input, it is not instantly update the output. Okay, it is not instantly update the output. Okay, because if you're given some voltage level and some processing time inside the gate, there can be some processing time. Okay, so you will have a delay to update the output. Okay, update the output. So if you are given some input, that is that effect come to output with some time. So that is called the propagation delay. Okay, propagation delay. And propagation delay also defined in low status and high status differently, separately. Okay, and if you want to find the average propagation delay, what you should do? You have to get the average of these two values. Okay, this propagation delay values. Okay, that means TPLH plus TPHL divided by 2. Okay, low to high and high to low propagation delay. You can add them. You can do. Okay. Okay. So these are related with the tri-stated logic gates. Okay. And this is also tri-stated logic gates. So you don't need to worry about that one. Okay. Okay. I think maximum clock frequency is already Okay. So I'm not going to do that. Okay. And the power dissipation. The power dissipation of the of a device is normally related with the in supply voltages and current. Okay, ICC and VCC. Okay, so if you get ICC into VCC, you will have the power dissipation. Okay, so can you remember that I have told you that when the voltage high, current can be low, and the voltage is low, current can be high. So that is happening. No, we have seen that. Okay, so that is happening because the dissipation power is a constant. It is ICC into VC. Okay, so you have given some constant ICC and you have a constant VC. Sorry, we can't say that constant ICC. Okay, because ICC can be changed. ICC can be changed. I'm sorry. We have given the constant VCC. Okay, so at that time, so for any instantaneous, Okay, any instant, okay, this our power dissipation will be ICC, instantaneous ICC into VC. Okay, okay. So at that instant, if your voltage is high, current should be low, no? Because you will have this power only. You can get this power. That is depend on ICC and VCC. Okay. So if you are given input to output voltage high or low, but you will have low and high current. Okay. Because this instantaneous value is constant. Okay. Okay. So here you have the fan out also. Okay. So I think this one also important. You have to get this. Okay. So okay, fan out. Yeah, so you can see that it is defined as number of inputs of a logic function that can be driven from a single out. Okay. So number of inputs for one output. Okay. Number of input for one output. That is called as fan out. Okay. So this fan out, okay, that means number of inputs per one output is defined, okay, through this output current. This output current you can see. Okay, so these are output currents. Okay. Okay, so we will do an example. You can understand this. Okay, so here it is mentioned some parameters with the CMOS logic device and TTL logic device. Okay, but you no need to refer these things. But for better understand, you can read. Okay, but if you know this term, that is enough. Okay, but you have to understand how this apply. Okay, so we will take example and clarify it. Okay, another very important thing is this one, noise margin. Okay, so we have to consider this noise margin also. Okay, okay, so to explain you the noise margin, I will take the TTL logic device as usual. Okay, so you can see that, I think you can remember that if we consider the output, okay, if we consider the output, okay, output, if you consider the output, um, if you consider the output, you will have, as I can remember, it is 0.4, no? 0.4 minimum voltage, sorry, not minimum, maximum so if you consider the TTL logic device, okay, there is some outputs, there is inputs, and there are some output ports. Okay, so input high level, sorry, I will take first output. Okay, so output high level, output low level. Okay, so this is output low level, V out low level. Okay, maximum, minimum, okay, is 0.4. Okay, and it is 2.4. Okay, we output high level maximum is 2.4 volt. Okay. So this is minimum, this is maximum. Is that correct? Is it correct? Can anyone feedback? Don't worry about this value, okay? I just write it as I can remember, okay? I'm not sure, okay, but I will explain the things, okay? So take this as 4.4 and 2.4. So, so my question is this the minimum or maximum? Have I written it correctly? I have written it as minimum, and here I have written it as maximum. Is it correct? Please feedback someone. Please think and feedback. I here write minimum and here I write maximum, max. Hear me. Is it correct or not? Can I proceed like this? So this is output low voltage level and this is output high voltage level. So please tell me. Couldn't you understand what I have explained later? Okay. So in a real circuit, we can't give constant voltage value. That voltage value can be changed. Okay. So different logic circuits have some margin value. Okay, margin value that is related with their fabrication property. Okay, we can't define it. It is in a, it can be decided in the fabrication process of the device. Okay. So some logic device, let's say that it is TTL logic device, you will have 0.4 voltage, low voltage. If it is 0.4, it is detected as low voltage. So it is minimum or maximum value. Please tell someone. That is very simple. මම මේ කියප එක තේරුම් නැද්ද ඔය කට්ටියට? ඒ කියන්නේ අපිට voltage level දෙකක් define කරගන්න පුළුවන් 0.5 කියලා. හරි. හැබැයි ඕක අපි circuit එක ඇතුලේ process වෙනකොට අපිට කියන්න බෑ ඕක හැම වෙලාවෙම constant කියලා. ඕවා වෙනස් වෙනවා. 0 සමහර වෙලාවට වෙනස් වෙනවා, 5 volt සමහර වෙලාවට වෙනස් වෙනවා. So we can't say that those are constant. Okay, those can be affected by noise, attenuation, and some distortion. Okay. Anyway, it is okay up to some level because normally, if you consider logic device, it have some margin values for low voltages and high voltages. Okay, so I have write the margin values for output voltage, low and high cases. Okay, is this minimum or maximum? What happen if this is more than 4 volt, 0.4 volt? What happen if this more than 0.4? Is it okay or is there any error? Can anyone tell me? If you get, let's say that 0.05 volt, is this voltage is okay or it create an error? Can anyone tell me? Can anyone tell me? Actually, it is an error, no? Because if you have 0.4 or loss voltage value, you can that device can identify it as low voltage value. But if you get 0.5 volt, you can't decide. Okay, so that voltage level will be error. Okay, so one voltage refer one bit, so there will be a bit error. Okay, so this is not okay. Okay, this is not okay. So actually this should be a maximum, no? This should be the low voltage maximum. This should be maximum 0.4. Okay. And 2.4, if you get more than 2.4, it is okay. But if you get less than 2.4, it will create again error. Okay. So this is not the maximum value. This will be a minimum value. Okay. So that will be a minimum value. Okay. So it is minimum. Correct. Okay. So this is maximum low voltage, output low voltage, and this is minimum high voltage, 0. and 2.4. Okay. So if you have any voltage between these two margin, okay, between two margin, you will get error. Okay. So this voltage is not acceptable. Okay. So when you are designing a circuit, you have to take care this one. Okay. Any voltage given between these two, it will create error. Okay. So that is why your actual implementing circuits are not working. Okay. That is what I want to explain you. Okay. Okay. So that is one. Okay. Okay. If you can't understand this thing, please ask me. Okay. Because these are very important and these are important for you. Okay. Okay. So it is I am talking. Okay, 0.4 and 2.4. Okay. So if you have any voltage between these two, it will create a problem. Okay, it will create a problem. Okay. Okay. And if you get the input, if you get the input voltage, in input also, there is a minimum high voltage and maximum low voltage. Okay. So there is a, this is input. Okay. Input. Okay. This is input high. Okay. So this should be a minimum. No, this should be the minimum. Okay. So as I can remember, it is 2 volt in TTA. Okay. And this is V input low. Okay. So that is the maximum value. As I can remember, it is 0.8 volt. Okay. Please check this value. Okay. Related with the TTA. Okay. So you will have this two. Okay. So you will you can see that the output, normally output range is big. Output range is higher than the input range. Okay. Output range is higher than the input range. So this is the output range 0 to 24, and this is the input range 0.8 to 2. Okay. So you can see that this one is greater than this one. Okay. Output is greater than the output range is greater than the input range. Okay. So normally in every one, I think it is same. Okay. As I know, I'm not sure. Okay. But I hope it is same. Okay. Okay. So what about this one? Okay. And you can see that if you have any voltage between these two, it is also a problem. You can't get, okay, in the input, that will be a problem. Okay. You can't at this point, if you have received this voltage level as the input, okay, so you will have some problems, no? Okay, so it is not detected as low or high voltage level. Okay, so you will have error. Okay, so this voltage level also we have to skip when we are designing the circuit. Okay, this voltage level and this voltage level. Okay, okay, so let's see. Okay, consider this one. Okay, and you can see that there is a gap between this and gap between these. Okay, actually these are defined as noise margin. Okay, these are defined as noise margin. Okay, so this is defined as high noise margin. Okay, high voltage noise margin. Okay, and this is defined as low voltage noise margin. Okay, so noise margin is nothing but the difference between VOH minus VIH. Okay, so this is the VNH, noise margin high voltage. Okay, VNH normally referred in this way. Okay, and this one is normally defined as noise margin low. Okay, noise margin low status. Okay, so it is VIL minus VOL. Okay, so this is the normally, so these are the normally noise margin we define. Okay, so can you try to understand what is the importance of this noise margin? Okay, so try to do it. Okay, so try to understand the importance of this noise margin. These are very important actually to detect the bits. Okay, so you have defined two noise margin. VNH, that is high voltage noise margin, that is between this VOH and VIH, and low voltage noise margin, that is VIL and VOL. Okay, so these are the noise margin we define. Okay, so try to understand the importance. Okay, so here you have a clear one. Okay, clear one. So you can see that this is so this is actually we have take as 0.4. This is take as 2.4. Okay, and this is 0.8, and this is 2 volt. Okay, so the VNH is here is equal to VOH minus VIH is equal to 0.4. Okay, and VNL is equal to VIL minus VOL, that is equal to 0.4. Okay, so these are the very small. Okay, so do you have another lecture? Can you give me another 15 minutes? Okay. Okay, so I will show you one data sheet. Okay, I will show you a data sheet. Let's say some, I think this one data sheet. Okay, so this is a 2-input NAND gate. It is 7400. In our lab, we have this NAND gate. Okay, so here you can see that 4 NAND gates are there. 4 NAND gates are there. Okay, and you can see that. So these are the parameters we have discussed. Can you see? Okay. VIH, VIL, VOH, VOL. Okay. So these are the propagation time. Okay. So can you see that? So this if you take logic gates, so these are in your data sheet. Okay. These are in your data sheet, and you have to use them in your design. Okay. Otherwise, you will get some error result. Okay. So now when you are designing your counter, you have to get this information into account. Okay. Otherwise, your system will be changed, will be not working properly. Okay. Okay. So can you try to do this example? Okay. Okay. So anyway, try to do this example by yourself. This one, okay, and this one, okay. So try to do this for example by yourself. Okay, and I will try to. I think these are you can understand by yourself. Okay, you no need my help to do this example because the process is there now. Okay, so you can easily do this. Okay, so try to do this example. If you can't understand one or two, so if you couldn't understand anything, you can ask me. Okay, so we will wind up here and try to do these examples by yourself. Okay, by yourself. Okay, so if you have any problem, you can ask. Okay, otherwise you can leave the meeting. Thank you for participating.